very happy to introduce Ananya Rao, who is a PhD candidate in Carnegie Mellon's Robotics Institute, working under the guidance of David Weddergreen and Howie Choset. And she is she's been around here at CMU for a while, which is great. Got both her bachelor's and master's degrees here, a bachelor's in computer science and a master's in robotics. And her work here in the disaster thrust, dealing with disaster robotics, is already generating a whole lot of excitement. Her research focuses on some really interesting areas, including motion planning, the coordination of multi-agent systems, and autonomous exploration. So she's particularly interested, looks like, in applications in space exploration and search and rescue. And so I'll turn it over now to Ananya. Thank you for joining us today.
Hi, everyone. Thanks for coming by. Thank you, Norm, for that introduction. Today, I want to talk in particular about some of the work I've done around coordinating heterogeneous multi-agent teams, particularly for disaster response. Like Norm mentioned, a lot of my work has been motivated by applications like disaster response and planetary exploration, where information gathering or covering your search region is a primary task or primary objective. And this can be true for a lot of different applications, not just disaster response and planetary exploration. Information gathering is also useful for things like agricultural applications, forest monitoring, etc. But my work largely focuses on disaster response and planetary exploration. And in this talk, I'm going to focus in more on the disaster response aspect. The other aspect of my work is trying to coordinate heterogeneous robotic teams for this information gathering. By heterogeneous teams, I mean teams of robots with different sensing and motion capabilities. These types of teams can help improve information gathering more than just using the same kind of robot, because different sensing and motion modalities can give us access to different kinds of information or different areas of your search space. For example, if you had an environment like this that had some trees, a ground vehicle could get under the trees and take measurements, while aerial vehicles could take measurements from above the tree cover. So the task that we're trying to solve here is the problem of information gathering. If you have some notion of where information of interest might be in your search space, and you have these different robots with different sensing and motion capabilities, how can you effectively cover this area and gather information? The way my work chooses to address this is by dividing this information gathering task into subtasks, which can then be assigned to these different robots. Particularly for disaster response, we also want to look at where these different robots should begin their trajectories so that they can effectively cover the space. This approach can be laid out diagrammatically as well, where we start with our inputs of the robots with their sensing and motion capabilities and some notion of where information of interest exists in our coverage in the area that we're searching. From this, we can identify deployment locations or starting locations for our different robots. We can come up with some kind of coordination strategy to have our different robots work together effectively. And then we can plan paths and execute these paths in order to cover the space. So to begin with, I want to talk about the specific kinds of robots I look at in my work. I abstract robots out to be their sensing modality and their motion modality. There are a lot of different attributes that can go into defining robot skill, but for information gathering, I've identified the motion model, or the way the robot can move in the world, and the sensing model, or the way the robot can read in information from the world, as two key elements. In particular, I look at motion models that could be curve constrained, or like the way you would drive a car, you have a limited turn radius, or omnidirectional, so you can like go in a straight line between any 2 points, and you can control the speed and the degree that you can turn and things like that. For the sensing models, we look at a point sensor, so you can only see something if it's exactly where you're standing or where the robot is, or a Gaussian sensor footprint, which means the center of this Gaussian, or the middle of a disk that defines your sensor footprint, you can see things with higher certainty, but you can still get some information from the peripherals of this disk. It will just be less confident. The other major input that goes into a lot of my work is something called an information prior. So an information prior is, we think of it as something that defines the amount of interesting information or expected information that you can find at each point in your search region. So if we were looking for people in this room, you would have higher values at each of like the places you guys are sitting, and lower values on the ground and the tables and the chairs, because we don't care as much about those parts of our region. In this talk, I'm going to focus in on two categories of information priors. The first being synthetic, where you place random Gaussians or prescribed Gaussians at different points in your search region. And those are the higher interest areas. So in these examples, the yellow areas are the regions of higher information, while the purple and the blue areas are regions of lower information. We also look at information maps generated from some real world aerial imagery. So these images are aerial imagery from Robin Murphy's group at Texas A&M, a data set called Cracer U Droids, which looks at aerial imagery of different disaster sites and also has building damage annotations of this aerial imagery. So we translate that into information priors by placing highest importance or highest information of interest at the most damaged buildings, a little bit lower at less damaged buildings, and then not as much interesting information at the non-building areas of this region. This is a little bit of an arbitrary decision that we've made, operating on the assumption that in these scenarios, what we want to observe are the damaged buildings. We could be looking for people, we could be like gaining more situational awareness. This could be changed depending on what the mission is. And the way that I will evaluate the coordination strategies and deployment locations that we algorithmically find is by planning paths for all of the robots in our team, executing them, and then seeing how the team does as a whole in terms of information gathering or coverage. To do this, I rely on something called the ergodic metric. The goal of the ergodic metric is to plan a trajectory for a robot that spends time in regions of your search area in proportion to the amount of expected information there. So time left to infinity, you'll go everywhere in the map, but you're prioritizing going to areas of higher interest or higher information, which makes this particularly well suited for the kinds of applications that we are looking at, which tend to be more time sensitive. The way that the ergodic metric does this is, given a trajectory for a robot, you can calculate something called the time averaged trajectory statistics, which just means what has the robot seen if you pass the sensor model across this trajectory that you've planned for it. And you compare this to the utility distribution or what you're trying to see with your robot or robot team. Here, for us, that would be the information prior. So the goal of the ergodic metric itself is the difference between these two distributions. And so the goal of ergodic trajectory optimization is to find controls for all of your robots, or planned trajectories for all of your robots, that minimize the ergodic metric or try to drive the difference between what the robots see and what they're trying to see to zero, subject to the dynamic constraints of your system. Here, that would be the motion models of your different robots. So you want to make sure that you're planning paths that your robots can actually execute. We also use the ergodic metric as a measure of coverage, since the lower the ergodic metric or the ergodicity value is, the closer these time average trajectory statistics and the information prior are, which means you've covered your space better. Okay, so the first section of work I would like to talk about is looking at how can we coordinate robots with different skills in order to effectively gather information or cover a space. I break this into two parts. The first being looking at how we can decompose this common task or this joint task of information gathering into subtasks, and then how we can allocate subtasks to different robots. There are three kind of factors or traits that we want out of an algorithm or an approach that looks at this. First, we want to take into account agent heterogeneity. We want to make sure robots are doing subtasks or are being assigned jobs that they are better suited to. We also want to decompose this one joint task that we have of information gathering with all of the robots into teams into more handleable subtasks. And then we want to intelligently allocate the subtasks that we have created to our different robots. So while there has been a lot of work done in multi-agent planning, a lot of that work has focused on planning paths for homogeneous teams, so robots that are all the same, and hasn't really looked at decomposing a task. There has been some work that looks at multi-agent, multi-objective ergodic search. So some work that ties to ergodic search, which is what we're building off of, or we use ergodic search as well. But again, this work does not look at heterogeneous teams, so all of the robots are the same. And there isn't a notion of decomposing a task, since the different subtasks here are these different objectives or different information priors that are handed to you as disparate tasks already. So while you are allocating different robots to these different maps, that allocation isn't driven by anything inherent to the robots themselves, and you don't have to decide what those subtasks are. Another category of work that looks at just doing the subtask allocation for predefined or already divided into subtasks work. You can use something called hierarchical clustering to do that for homogeneous agents. Once you start looking at heterogeneous teams, there is some work in the using the leader follower approach, where you assign one of the robots as the leader and it allocates tasks to the follower robots. However, in this work, typically the tasks or the subtasks are different goal locations. So there isn't like a shared joint task that you're trying to decompose, or you assume that a human or some other process has already split up your task into subtasks. And similarly, once you have these subtasks already split up, either because they are goal locations and so they're already disparate, or because you have some person or some other system that is dividing those tasks for you, you can use one of several different auctioning mechanisms to auction off these tasks to different robots. Again, neither of these methods really try to leverage or lean into agent heterogeneity, particularly as it relates to whatever task they're trying to solve. There has been some work that looks at both decomposing a joint task and then allocating those subtasks to different robots, but it has been terrain-based. So this work on domain decomposition and generative allocation has looked at a heterogeneous team that's heterogeneous in terms of what spatial areas of the map different robots can access. So you can think of a boat and a car-like agent being paired together. The boat can only go in water, the car can only drive on land. So you decompose your search task based on the kind of terrain you would be traversing, and then match those subtasks to the robot based on the terrain that they can handle. My work looks at using something called spectral-based allocation to both decompose the information gathering task into subtasks and allocate them to different robots. So to detail that, first, I will talk about how we use spectral decomposition to divide a task, or here, information gathering, into subtasks. So we use spectral decomposition to create these subtasks, which another way of thinking about this is we divide this spectral or this information map into different spectral scales of information. We use Fourier decomposition to do this. So we start with our information prior, use Fourier decomposition to get the frequency space representation of that information map. So encoded in frequency space, the spatial distribution that's on the left looks like this distribution of bars in the middle. Here, the x-axis is different frequencies or spectral bands, and the y-axis is the coefficients or the weights on those frequencies. So depending on what your information distribution looks like, this frequency space representation of it will look different. I will note that the frequency space representation does not encode spatial information. So a map that had a high information dense blob in the bottom left corner would look the same as one that had one just in the top right corner in the frequency domain. But you can pull out subsections of the frequency space representation and then map it back to the spatial domain to create these subtasks or information maps at different spectral scales. So here, if you reconstruct an information map with just, let's say, the first 5 frequencies, you get something that looks like this top right image. That's a more like broad stroke, blurred out version of your full information map. And that reconstruction looks different depending on which section of frequencies you choose to use. So as another example, if you reconstruct an information map from your highest order frequencies or like the far right set of frequencies, you get an information map that looks like this bottom right corner one that has more of the like pinpricks of high information, but is also noisier. So now that we have these different subtasks or different sub-information maps that could be assigned to different robots, how can we allocate the robots to these subtasks intelligently? One way of doing this is by relying on human intuition of what different robots are good at. So let's say we have a 2-robot team. One of the robots is a drone that has a very large sensor footprint, but it's not a very like high resolution sensor. And it's fast and can do an omnidirectional motion model, so it can cover a space quickly. Our other agent is a ground vehicle that has a smaller, more precise sensor, but also a slower curve constrained motion model. So intuitively, we might say that to cover a space, we would want the drone to quickly fly over the entire area and get like a coarse understanding of the information there, while we want the car to drive between these points of higher information to disambiguate them. We could elicit that kind of behavior by having both of these robots conduct their ergodic trajectory optimization by using these individual information priors, respectively, instead of the original information prior. So for the drone, because it's now planning a path based on an information prior that has this blurrier broad stroke information, it will tend to conduct a trajectory that is more of a broad stroke coverage of the region. While the car, because it's based off of this map that has these higher points of information, will try to drive between them. We evaluate this kind of allocation experimentally and compare it to 2 other forms of agent allocation. One is random, where we divide the information gathering task into these spectral subtasks, and then randomly pick one for each type of robot. The other form of allocation that we consider is adversarial. So we just do the exact opposite of what the kind of allocation we would do in the intuitive case. We ran these experiments on teams of 1 to 25 robots, and we used 2 performance metrics here. The first is ergodicity. Like I said earlier, we use that as a measure of coverage performance. The lower the ergodicity, the better the team has done covering the search space. The other metric that we use is the time taken to find all objects in the search region, and we use that as a measure of search performance. So first, in terms of coverage performance, we see that using our intuitive allocation method, we get approximately a 40% improvement in coverage performance over a baseline method of doing no allocation. So if all of your robots were listening to the same initial information prior, everybody's just planning a trajectory together. Doing this kind of intuitive allocation of subtasks leads to about a 40% improvement over that baseline. But we see that this improvement doesn't come just from the idea of splitting our information gathering task into subtasks, but the way the allocation happens is very important because our random allocation and adversarial allocation methods do not perform better and in fact perform worse than doing no allocation at all. We see a similar trend in search performance, where the intuitive allocation method has about a 15% improvement in search performance. I will note that there's nothing in our method that's explicitly optimizing for search performance. The improvements in search performance are sort of a byproduct of improving coverage performance. If you're spending, if you're being smarter about how you're spending your time covering the space, you are also more, it seems more likely to find objects that are in these areas of high interest. So while this intuitive allocation method does give us performance improvements, it is still reliant on having a human understanding of what the robot is good at doing. So we could only assign the drone to do something it was better at, search-wise, because we understood the kind of trajectory we would want it to execute. Which works fine if you have simple robots and simple environments, and starts to fall apart as soon as any of that becomes more complicated. So instead, what you can do is learn this allocation of robots to subtasks. I won't go into the details of how we do that learning, but at a high level, we use an actor-critic network to learn an assignment of robots to frequencies. And we do this in 3 different ways. In the first, we divide our frequency space into predetermined buckets. And the learning that's happening is we're learning a mapping of robot to one of these buckets. So here we're sticking with the same 2 robot example of the drone and the car. The blue is the drone, and we see that it learns to map itself to the lowest order frequencies, which matches the intuition that we were using earlier. The car, or the red robot, ends up mapping itself to the highest order frequencies, which again matches our intuition. This method still requires some handcrafting, like someone has to decide what these buckets are. So instead, we can directly learn weights over all of the individual frequencies for each robot. We see that the same trend happens when we do this, where the blue robot or the drone tends to favor the lower order frequencies, while the red robot or the car tends to favor the higher order frequencies, but it's not as like bifurcated as we had been operating. So while this gives the robots some more granular control over what their subtasks should be, you are learning so many more numbers here. So an in-between to both of these is to learn parameters that define a curve over your frequency weight. So you're learning fewer numbers, but you're not stuck to just picking from a set of predefined buckets. And here again, we see that the drone tends to pick the lower order frequencies and the car tends to pick the higher order frequencies, all of which verifies the intuition that we were using before for this simple case. We evaluated these methods, again, experimentally on teams of 1 to 25 robots, using the same 2 performance metrics for coverage and search. So in the first case for coverage performance, we see that all 3 of the learned allocations perform better than the no allocation, or the dot on the far left. And the performances are fairly similar for the intuition-based allocation. These experiments were still run on robots and teams and environments where we could have an intuition-based allocation so that we could do this comparison. So we would expect that the performance is similar. I will note that learning weights over all of the frequencies directly does outperform either of the other 2 methods by a little bit, but it does take longer to train just because your problem complexity has increased. And again, we see the same kind of trend in results for the search performance in terms of the time taken to find all objects in your search space. Okay, so now that we know how we can coordinate robots in a heterogeneous team to explore and gather information in a space, I want to talk more about how we can pick where those robots start. This is an important aspect, particularly for disaster response, because thus far we've been assuming that any of our robots can start operation at any point in your search area or any point in that information map. This is very much not the case for an application like disaster response, where you might not even be able to access or physically get your robot to all of the spaces in your information map. So here we look at this problem that is very complex in 2 simple steps that we have started to address. The first looks at providing an algorithmic recommendation of base of operations locations. This aspect could apply to both human rescue teams and robot rescue teams. And then the other part is looking at optimizing start locations for our robotic agents. This is an important question to answer because the starting location selection and base of operation selection right now largely happens by expert decision, like emergency managers in the room decide where these assets should go. However, particularly for robotic agents that are exploring a space, the quality of their exploration pads is limited by starting location because they have a limited operation time. They can only get to certain parts of the map so fast. And so where you start operations does matter. But taking a quick step back, I first want to talk about our method of creating a recommendation of where base of operations should be set up in a disaster site. This is work that one of my interns, Alyssa, did over this past summer. We make a couple of assumptions in this work. First, we assume that we have access to aerial imagery of the disaster site. This could come from satellite imagery, or in our case, from aerial imagery out of, again, the Cracer U-Droids data set. We also make some assumptions on what factors are important to consider for base of operation selection. This came from federal guidelines for how like FEMA picks these base of operations right now. But again, this could change based on state guidelines or just the emergency manager in the room. So for our algorithm, we consider four main factors for base of operation prioritization. The first is what class or what category a certain region of the map is in, or a segment of the map is in. So we say that fields are better base of operations than roads are. We also then look at the area of these fields. So a larger field would make for a better base of operation than a smaller one would, because you can set up more there. Third, we look at accessibility, or is there a road that we could drive on to get to this base of operations? And of course, an accessible base of operations beats out an inaccessible one. And finally, we look at the reachability of that base of operations. So in these pictures, the bright green areas are base of operation candidates. The red, yellow, and blue squares in the upper image are the overlay from the building damage annotations from Texas A&M's group that I mentioned earlier. And we're saying that having a base of operations that is closer to these damaged buildings is better, or a base of operations that has more reach to these is better than one that has less reach or is less close to these damaged buildings. Again, this is operating on the assumption that a goal of this exploration is to evaluate or survey these damaged buildings, and that would change if it was a different goal. So we feed that into our algorithm. We put weights on these different factors and do a weighted sum. So in this simplified example, even though option 1 is larger than option 2 is, and there are roads near both of them, option 2 wins out in our scoring mechanism because it is closer to more damaged buildings. The idea there being if you set up like a drone team there, it would, or whatever kind of robotic agents you had there, it would be easier to get to the higher damaged areas that you're trying to inspect or evaluate or whatever. To step through our pipeline, we start with aerial imagery that we segment to pull out the fields and the roads in particular. We can then overlay the building damage annotations from the Cracer U-Droids. We evaluate the segment class or category, the area of the different field segments, and the accessibility to the different field segments, and we come up with like a ranked list based on our scoring mechanism. We also have a ranked list of the reachability scores based on the building annotation. And then we can put that together to come up with a final scored list of base of operation options. So the idea here is that if you want a fully autonomous system, you could pick the first ranked thing. But you could also hand this to an emergency manager and they wouldn't have to step through all of the evaluating and putting together the data themselves. They could just look at this and go, all right, I want to go to place 2 actually, and go from there. And like I said, because all of these decisions are most of these decisions are currently made by human experts, we did survey 11 California disaster relief volunteers and Air Force search and rescue responders with the goal of figuring out what base of operations they would pick for these scenarios, what qualities or factors influence that decision, and whether they preferred operating off of this annotated picture that we handed them with our recommendation list, or just the aerial imagery, or just the building damage annotation imagery. And from this initial survey, we see that they did tend to prefer having the fully annotated with recommendations version of imagery to make decisions off of. We also see that the majority of the time, the base of operations that the experts picked aligned with the one that our algorithm picked as the top priority or the highest recommendation. And this stayed true across different examples. Examples like this, where there were multiple highly ranked candidate locations in a similar area, had more variance in what the humans picked. And that is a little bit because there wasn't really a consensus in what factors people thought were most important. Everyone agreed that accessibility and proximity to things of interest were important, but how important those two things were in relation to each other differed person to person. Okay, so identifying or recommending where you should set up a base of operations could be applicable to both human teams and robot teams, but coming back to exploring a space with a robot team, we need to know where we should start these different robots. Again, we've been using ergodic trajectory optimization to plan our paths, and so far, the only constraint that this optimization listens to is these dynamic constraints to make sure that the robots can actually execute the paths that are planned. We assume that we can start anywhere in the search space, but if we wanted to constrain that, we could add into this optimization problem a constraint that said that all of our start locations have to be within a predetermined viable starting location set. And this can be a different set of options for each type of robot, which allows us then to have different types of robots in this heterogeneous team to start at different locations that could be better suited to the subtasks that they care about. To experimentally evaluate this, we compared 3 baselines. The first is starting all of our robots at a single random starting location. The second is starting robots at different random starting locations. And the third is starting all of our robots at a single optimized starting location. So we are still adding in this constraint that our starting locations have to fall within a set, but we're saying all of the robots will start at the same place, and as long as that place is within a viable starting location, we're good. We also make quite a few assumptions in this work. The first being that we have access to these potential or viable starting locations for each type of robot. For this work, we do rely on the base of operation recommendation algorithm that I was talking about earlier to generate this, but this information could also come from experts. We also assume that these potential starting locations fulfill all required criteria for the type of robot that they are viable for. So this means that the terrain available works for setting up a drone-like landing zone. It could mean that the roads are wide enough to drive in a truck that's carrying your ground vehicle, or to drive in your ground vehicle. It depends on the type of robot. We also assume that all of our robots start operations simultaneously. Now, this is a big assumption to make because in the real world, you could have different starting times because of the time it takes to transit to your starting locations, because of different communication issues, whatever. But for this initial approach, we do assume that all of our robots start executing their paths at the same time. So for this, we did run some experiments on homogeneous teams as well. And for these, we see that whether you optimize for a single starting location or multiple starting locations, you get similar performance. And that does outperform having random starting locations. The similarity in performance for single and multiple optimized starting locations here makes some sense since all of your robots have the same skill sets. They wouldn't have, starting them at different locations really just spatially spreads them out a little bit, which helps a little, but not a ton. However, when you run experiments on heterogeneous teams, having multiple optimized starting locations does start to have an impact on performance and outperforms having a single optimized starting location. And this is because once you allow your algorithm to optimize for multiple starting locations, you can pick a starting location that is best suited to a robot and the specific subtask that it is trying to solve, as opposed to trying to find one starting location that is good enough for everyone. Okay, so in summary, my work looks at how spectral-based task decomposition and agent subtask allocation improves the team's overall information gathering performance. We also see that starting point optimization further increases the coverage performance of heterogeneous teams. And finally, we see that base of operation prioritization and starting point optimization can increase the deployability of heterogeneous teams by starting to bridge the gaps that we need to cover to actually deploy any of these in the real world. Now, there is a lot of future directions and interesting future work that could be done. One that I am particularly excited about is continuing user evaluations on the starting point optimizations and base of operation recommendations at a tabletop exercise being conducted by AI-SDM in a couple of months. Like I said earlier, relying on the Fourier decomposition for all of our subtask creation and allocation does mean that we're throwing out spatial information. We incorporate some of that back in a little bit by adding in the starting point optimization, but there are a lot more interesting things that you could do to incorporate spatial information more intentionally. We also assume in all of this work so far that your environment is static, which is not true in the highly dynamic and volatile world of disaster response. And so adapting these methods to address dynamic environments would also be very interesting, as well as adapting these methods to incorporate additional real-world costs, like the cost of transiting to starting locations, the cost of transporting any of these robots to anywhere at all, operational costs generally, etc. I'd also like to acknowledge all of my collaborators on this work, in particular, Alyssa at the Air Force Academy and Guillaume at the National University of Singapore, as well as AI-SDM for funding a lot of this work and providing a lot of great collaborations. And in particular, a shout out to Tom and Priya and Robin at Texas A&M and their Cracer Droids data set, which has been game-changing for the work that I've been able to do. And yeah, that is all. Thank you all. Questions?
Good question.
Yeah.
So you talked about determining the best, maybe the most ideal base of operations. Right?
Mm-hmm.
And it seemed like your method was in pretty good agreement with what the experts were saying.
Mm-hmm.
Do you have a sense of how much time, effort, cost is involved with those experts getting to that decision?
That is an excellent question and one that I'm not entirely sure how to gather the information on. Hopefully that's something that we can get from the tabletop, but for the survey, we were trying to make it as low effort as possible. So that's why it was like set up as a grid, and it was a small image with a grid, and it was just pick a box in this grid, which is obviously not how they do anything in the real world setting.
So the survey was just based on like a picture?
Yes, it was based on this aerial imagery from Cracer Droids, and what they were handed was just the picture with this grid overlay and told, where would you set up in those operations here, versus being shown like the full annotated with recommendations version. And we just asked, like, would you prefer having the annotation? As opposed to having any kind of quantitative measures on like how long would it take you to make a decision without the annotation.
Yeah, so do they get, do they typically get information about, I don't know, what would be the relevant information, like road passability or whatever? Like part, or are they literally just like, oh, like, here's an open field, do we go there? Like,
From conversations, and this is a very small sample set because it's just these 11 folks that I got to talk to. It sounds like the answer is it depends wildly, but they do start off with a like, we have some initial imagery, we have some initial information from people on the ground. We think if you go set up in this corner, you're not in anyone's way. Start there. But this is very limited information.
So, well, that's an very interesting point. I would imagine, although I've never been in a real response scenario, that everyone's making quick decisions. Spot on decisions. So we're never gonna have this kind of case where someone's gonna take a while to figure something out. So, and then on top of that, I don't think we'll ever get people the patience as a student support to spend time to figure something out either. So I think what would be interesting would be, can we create scenarios where the spot decision doesn't give you a good answer and none of this stuff does? And I would imagine as you have more and more agents, that's when that would happen. But that's really, that would be cool.
The current line of work to make methods like this, sort of adaptive to dynamic.
So my first pass at it, or my first thought around it is if we make replanning and reallocating low cost or fast, then you could just update your maps as they change and reallocate and replan as you go. That is definitely, I think, the like easiest or most straightforward way to make this adaptable to dynamic environments. What would be very interesting is if there was any degree of predictability in how these environments change, putting that into the framework as well, so that you could like reason about what the state of the environment might be 10 minutes from now instead of reactively reasoning.
Do they have any feedback or suggestions on it?
Maple sugar. Also kind of wondering, like, you know, I don't know how familiar you are with like Paul Lehner's work in these. Talks about looking into like adoption and when schools are like actually used. I know that we're not
Yeah.
maybe at that step yet, but I'm just wondering like, what is the most, do you have any thoughts on like, I'm thinking about like use patterns, like, would you, like, when these experts were doing this, analysis of their preferred base of operations, is it, most useful for them to get the AI input first or make their own decision, then look at the,
Yeah, I
recommendation?
think that one also differs person to person. So I think the like best way to have this or like an AI or an algorithmic recommendation system be a part of that decision process is to have it sort of passively as another information input that they could consult should they choose to. And I also think that is having that kind of setup is the best way to get people to agree to have this in the room in the first place.
Yeah.
Instead of being like, well, look at this first and then make a decision.
Any other questions from the group here in person? All right, if not, well, thank you, Ananya.